Good morning, everyone. Welcome to my third talk this time. Yesterday we talked about C# 7, the new features in C# 7 and 7.1. Afterwards, we talked in the afternoon, I believe, we talked about C# language internals. This is another one of those talks where we're going to take a look behind the scenes, not of C# in this case, but we're going to take a look behind the scenes of .NET Core, the core libraries, as well as the core CLR. So again, usual warnings apply. This is a level 666 talk, so we're going to go deep. I don't know where we're going to end up. I don't have a menu this time. We're actually just going to do source code browsing. And if there's anything that you should remember from this talk, it's actually everything to do with the strategy around .NET Core and the C# language design and the Visual Basic language design. All of that stuff is now happening out in the open. So the key message here is that I'm really convinced that as a developer, if you want to be, outstanding in your company, that you should be one of those developers that's on the cutting edge and that also understands how things work. In fact, what differentiates, a lot of, regular developers from hardcore developers is that the latter camp actually knows, the technology they're using and how it kind of works internally. And that doesn't mean that you have to go super deep, but it means that you have at least some solid understanding where you can find stuff. And that has become much, much easier now that everything in .NET is open source. So I'm just going to start by highlighting a couple of places to go, and then we're actually going to jump right in. In fact, later on in this, at this conference, I have 2 more talks. I will actually be talking about .NET performance later today, somewhere around 11 o'clock, I believe. There we're actually going to go not really behind the scenes, but I'm going to explain a bunch of performance caveats that we ran into in building a high-density cloud service in the Bing backend where I'm currently working at Microsoft. And that, of course, also involves, browsing source code at some point to figure out, like, why doesn't this thing perform the way we believe it would. And later I will also talk about Roslyn, how to build your custom plugins. Again, one of those things that now you have all the source code available is much, much easier to figure out how things work. And so this should be our homepage. If you have any other homepage today, you're doing it wrong. You should totally have github.com/.net as your starting page. And so the 2 repos that I'm going to take a look at today here is CoreFX and Core CLR. Yesterday we actually looked briefly at Roslyn. I actually cloned the Roslyn repo in order to be able to step through the compiler source code. So that's where you find the C# and Visual Basic compilers. And there's a whole bunch of other ones here. Those are the pinned repositories. You see that there's a whole lot more repositories over here. One that's pretty important as well is C# lang, where you find all the language design notes. So we're going to focus on the first 2. What's in those 2? CoreFX contains the core framework, so you'll find libraries like system.collections in there, system threading tasks, system.link, all of that stuff is over there. And then Core CLR is the repo that contains the common language runtime that's actually portable against a whole bunch of operating systems, including Windows and Linux, for example. And so that's actually the core library. It also contains a little bit, that's the core runtime. It also contains a little bit of core library code, which is the thing that you know as MS Corelib. We'll actually take a look at some of the code in there as well, because that's code that's actually highly dependent on the implementation details of the CLR. But if you look at this, you can already see, well, actually you can't see it over here, but if I go to CoreFX, CoreFX should not be something you should be super afraid of looking into, because if you click over here, you see it's 97.5% done in C#. All of the core libraries are just using our own dog food. They're all written using C# themselves. You see over here a little bit of, C and C++ and 1C Enterprise. I don't know what that is. I think somebody used some extension that's recognized as such, but like largely C# over here. If you go to Core CLR over there, there's still a whole lot of stuff here that's actually C#, so that should totally be in the comfort zone. But then, of course, the core library or the core runtime is actually implemented largely in C++. There's also a little bit of C code there and a tiny bit of assembly, because ultimately this contains a just-in-time compiler that has to turn your code into native CPU instructions. So that's kind of, to see how this thing is kind of composed, okay? So let's get started maybe a little bit in the comfort zone of CoreFX. So what I've done is yesterday, I actually cloned the repo over here by just copying this, do a git clone. I did the same for Core CLR. I built those things locally so I can actually run them locally. But the main incentive for me to do that was to actually be able to open all of the code in Visual Studio Code so we can actually see it with some syntax highlighting as opposed to just being clicking around on the GitHub website. And so here we have all of CoreFX, all of the code in CoreFX, and I'm just going to point out a couple of new types and just walk through a little bit of the code with you, just to get you into this feel of the barrier to entrance is really low. You just git clone this thing, you open it over here, you start browsing. So one of the new things that we have in .NET Core, for example, and let me actually point out this thing first. In .NET Core, there's a bunch of things that we want to achieve. One thing, of course, is to be able to be ultra portable. And in order to make the platform ultra portable, there's a bunch of things that have to happen. One thing that has to happen is to make sure that the CLR can run on different platforms so that we're not tied to the hip to, for example, Windows assumptions. We'll see later, for example, that the garbage collector has to do a lot of things to actually work with the different allocators in different operating systems. A second thing that's super important to us is make sure that .NET is actually a great platform to run server workloads and have high performance scenarios as well. Historically, .NET has been doing a lot of things, ranging from desktops to mobile applications to servers, and there was not really that much attention to high performance server scenarios in the same camp as, for example, Node.js, where you also want to have very lightweight, low startup costs and be able to serve lots and lots of requests at the same time. And so you will actually find that there's a lot of stuff happening in .NET Core that has to do with performance. And so one thing that's actually readily usable for you as well, and that's actually being used in a whole bunch of places inside the .NET Framework now and inside .NET Core, is pools in system.buffers. So what this does is, well, one of the main things that can cause performance issues is, of course, allocating way too much stuff. We have a garbage collector. The garbage collector does a great job in getting rid of garbage, but the best way of actually making sure that your application is highly performant is to avoid creating a lot of garbage that's unnecessary. And so one of the things that's very useful, for example, is array pools, where you can actually say, well, let me allocate some array, and then I want to use that array multiple times, for example, to do things like reading data from I/O into a buffer, then look into that buffer, use the values that I've just read, and then return that array to the pool so it can be reused at a later point in time. So you actually create far less churn in allocations and garbage collections that need to happen. And this is actually a type that has a very simple interface over here. It actually has a shared pool that can be used, so you can just do array pool of T, where T is a generic type, .shared. You can also create your own ones over here using the factory method called create. And then there's only two operations that you really want to use over here. One is called rent, and you see it's not that you want to rent an array of a certain capacity, you basically specify a minimum length. So if I say give me an array of length 100, you may get one of length 256 or something, or 128, or whatever number is available in there. You can actually use that array then, and once you're done with that array, you give it back to the pool by using return, and you can optionally ask us to actually clear the elements in the array. And so that way, we can actually keep a bunch of arrays of a certain type around so that we can actually reuse them. And you basically say, like, I want an array of at least this size because I want to feed it into some API, like, for example, the read API in system.io. So that's one example of something that's new in .NET Core. Let me actually also talk about something else over here. Let's go to system.memory. Not going to go into too much detail about this, but just to emphasize that performance is a very big theme in everything we're doing in .NET Core. System.memory contains a bunch of new types that can actually be used for high performance scenarios that actually can also reduce memory allocations. And so a new type that you will start seeing appearing in some APIs, step by step this will serve up in more places, is the span of T API. And so span of T API is a way to actually represent in a memory and type-safe manner data of a certain type, a contiguous region of memory that actually is associated with that particular type, so you can actually read it as such. And it's also a way of actually getting slices. If you have an array of a certain type and you want to get a section out of it, you can actually get a slice out of it, which is very similar to array segment, which we had in the past. And so what this allows you to do is, for example, I'll give you a concrete example over here. This is a blog from Adam Sitnik. He's actually somebody in the community who's super active in the .NET Core world as well. And so over here is a good set of examples of the span API. And a very concrete example that I'm just going to point out here is, say that you have a string, which is really a character array. Rather than doing substring, which is something you may do in a request serving pipeline, you're sort of going to look at the string that comes in and you're sort of going to lex it and parse it and take out a section. When you do substring, you're doing a new allocation. So what you're going to see is that we'll have much more APIs that take in spans, so that you can actually pass in a segment, a little view over a contiguous region of memory, and then pass that to APIs. Things, for example, like int.parse may get at some point segments into strings, so you can actually say parse this piece without first allocating a substring that contains the number that you want to parse. So you will basically just be reading one time a big string. That will be causing the allocations. Ideally, we will actually be using buffers to get a character array of the appropriate length as opposed to allocating a string. And then you can actually start looking at views in that thing in a memory-safe way. And so span of T is one of those low-level APIs that will start showing up in a bunch of places where if you have a span of T available, you should not create some performance crime by actually taking out all of the data and then heap allocating it somewhere else. You should try to stuff that span of T deeper down into APIs that actually take it, and you will actually get much better performance out of that. So you will start seeing more of those kind of APIs, and they're very fluent to use. They have nice operators on them, equality and those kind of things. They feel very natural as well. Okay, so that's another thing over here. Now let's also show a few interesting other features. First of all, I'm going to show you the value tuples that we were talking about yesterday in C#7. And I just wanted to point them out because there's a couple of things that stand out. And I just want to re-emphasize them because they also fit in the theme of performance. First of all, what you see over here is that all those value tuples that we have are structs. So they're actually stack allocated, or they just live wherever the containing object lives. So for example, they can be completely embedded in a heap allocated object in a field, for example. So they're high performance, and they also have mutable fields. Now you will say, well, structs that are mutable, isn't that a bad thing? Well, in this particular case, it's a great thing. You want to be able to just, pass those things around, low overhead, just be able to get access to those fields. And, they're typically used for passing of data, from A to B. So that's actually one of the reasons that this thing is organized this way. The second thing that I wanted to point out about this thing is that, let me see if I can find it. This thing also supports, of course, creating hash codes. And god damn it, here we go. What we have over here is something called combine hash codes. And I guess pretty much everyone has overridden get hash code at some point. Let me actually try to find the definition of this thing. I didn't load the whole thing. Oh my god, where is it? Doesn't matter. I'll just go to hashing helpers, which is the core that this thing calls into, hash helpers. But so here you start seeing optimizations, performance optimizations being documented in a very particular way. What you see over here is to combine two hash codes. One thing you shouldn't do if you look on Stack Overflow and you ask, how to combine two hash codes, some people will say they just use an XOR or just added two things up. Well, that's not a good thing to do, because then your hash code is actually independent of the order. Like if you have say for example a value tuple with 2 ints, and you just add the hash code of the left and the right together, then that will have a collision with a value tuple that has exactly the same things but in the opposite order. Like 3,4 and 4,3 will collide to the same hash code. So you need to do something better, and traditionally people have done things like multiply with prime numbers, add things together, blah 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 kind of things. But one thing that's also super effective is actually to do a rotation of bits. What that just means is that you have one hash code and you shift it by 5 bits, and then you do an XOR with the other hash code. So you sort of overlay the two, but you offset one from the other. And so what you see over here is something, well, C# doesn't have something called rotate bits. We have left shift, we have right shift, we have XOR, we have all of those kind of things, but we don't have, a rotation thing. Well, it turns out that the JIT compiler has been optimized to recognize a whole bunch of patterns. And in fact, it already recognizes a whole lot of patterns in desktop CLR as well. For example, when you do enumerations over data structures or strings and arrays and those kind of things, it can eliminate a bunch of range checks and all that kind of stuff. Well, in this particular case for hash code combinations, which can be very intense, for example, if you use this as a key in a dictionary, we have to do a lot of hash code computations. A lot of performance is to be gained if you can make that super efficient. And so what you see over here is that whenever we combine hash codes in a whole bunch of places, in the .NET framework we'll use this little trick. So what you see over here is that we do a left shift with 5 bits, a right shift with 27 bits. It's not a coincidence that the sum of those two things is 32. So we know that we are not losing any of the bits. We're just shifting things to the left, shifting things to the right. We still have all of the bits available. And this turns out that the CPU actually has an instruction called rotate left and rotate right that can do exactly that. And so what happens is that the JIT compiler sees this pattern and will actually turn it in a single CPU instruction, which is super efficient, as opposed to doing a whole bunch of multiplications with prime numbers, which is much more expensive to perform those multiplications. And so over here, and that's the interesting thing, is that as you start browsing the .NET code, we'll start seeing much more references to links, on the GitHub site where we actually have the issue that introduced this particular optimization. And then you can also find the commits, and you can see what code has changed and how this was implemented. So you can actually start doing archaeology in the source code as well. Okay, so that's the value tuple stuff. I just want to point that out really briefly. There's this folder common over here. The common folder is actually a bunch of CS files that are included in other projects. So this code is literally copied in a bunch of places so that this doesn't become, like this originally comes from system.numerics, like things like big integer and stuff. Well, we don't want value tuple to be dependent on system.numerics. So this is something that kind of everyone wants to use, but we don't want to make it public, just yet. Maybe at some point it becomes public. But so what's happening here is that we have a set of files that can be included ad hoc in a whole bunch of other places of the .NET Core platform. Okay, so that's actually the value tuples, just very briefly. One thing that I want to point out as well is that yesterday I actually talked briefly about those tuples having names. You can actually give names to the different components of the tuple in C#. And so the way that, whoopsie daisy, what's happening here? How long has this been going on? Okay, good. Otherwise I have to rewind. Reset the clock, please, to 45 minutes. Help! They're sleeping down there. Hello. I'm here. Oh, yes, yeah. There's no video anymore. No. Yes. They're gonna come and help. In the meantime, all gather around over here. I'm gonna look over the laptop. I can talk a little bit in the meantime while they figure this out. Okay. So, tuples. And this is kind of annoying. So, value tuples. You can give names to those identifiers, right? You can say, like, the first component is X, the second component is Y. And it actually compiles down to value tuple of T and T1 and T2 and T3 and so forth. So, we just translate those things into value tuple generic types. Now the problem is, of course, that when you erase stuff like that, you just get rid of, this compile time knowledge of like the identifiers, and you just turn it into standard value tuple. At the runtime level, we only have item 1 and item 2 and item 3 and item 4, those things available. And in fact, if you have a super large tuple, we'll do nesting. Ah, there we go. Very good. So the problem is that when you write something in C#, you say, like, I have a tuple here and I want to do .x. There is no x field or property available that we can bind to. So we still want to have full fidelity as you return a value tuple out of an API and you consume it in a different library. We still want to remember that this thing is called X and that thing is called Y and so forth. So we have to sort of keep those names around, but we don't want to be generating unique tuple types everywhere, because then there's no assignability, between different tuple types that have exactly the same shape but different names. It would also cause a lot of code bloat. So in order to support that, the compiler will actually stick a tuple element names attribute on a lot of places. So if you take in a tuple, for example, we'll actually annotate the parameter in that method with tuple names, which is actually an attribute that contains, of course, an array of strings, which contains the different names of the components of the tuple. And in a very similar way, we'll do that when we return something out of a method. We'll annotate the return type and so on. So that's the way that those names actually flow across API boundaries so that you get full fidelity. But behind the scenes, when you look in ILSpy, you will just see that this thing compiled to .item1 and .item2 and item3 and so forth. But we just give you, a convenient way to refer to those components. And so that's what's happening here. And you see that this small assembly containing the value tuples contains all of the value tuples declared in the system namespace over here, but it also contains the companion types that are required by the compiler in system.runtime.compiler services. So that's that attribute in this particular case. Okay, one last thing in CoreFX that I wanted to point out. It's something that's dear to my heart because the service I'm building in the Bing stack is using this thing all over the place. That's system.link.expressions. How many of you know system.link expressions? A good body of people. So system link expressions allows you to represent code at runtime as a data structure. And that's the thing that was introduced in .NET 3.5, C#3, and VB9 as part of LINQ, Language Integrated Query, to be able to support query providers. So when you write a query expression in LINQ to SQL, it gets captured as an expression tree, and that expression tree can then be translated, for example, to SQL statements. Now, what's interesting is that expression trees also contain support to compile those expressions. So if you go over here, let me do Control P to get to that file. Let's say lambda expression. We have a compile method in here somewhere. There we go. So you can actually take a lambda expression and compile it. So at the runtime, we'll generate IL instructions that can get JIT compiled, and then you can invoke that expression tree. I have a small example, not over here, I will rewrite it, but say you have an expression of func of int, and you want to return 42, you can actually at runtime manipulate this data structure. You can get to the body, do all sorts of optimizations, rewrites to that. But at some point you can say, let me actually compile this thing, and out of it comes a func of int, let me call it g. So now I can invoke this thing and it will return 42, which is the answer to everything. So here you go. So that's what you do. Now, compilation of expression trees is quite expensive, and secondly, compilation of expression trees is not always available. In fact, if you have Windows Store applications, we don't want to have JIT compilation at runtime there for a variety of reasons, security, battery, those kind of things. So you actually need to have an alternative way to still support this API. And so as part of being able to run these things in constrained environments, we had to introduce also an interpreter for the expression trees. And that's something that's happening in a bunch of places in .NET, where we can either JIT compile things or we can actually interpret them at runtime. Now you will say, well, interpretation isn't that slower? Well, I'll tell you a couple of things about that. But first of all, how do you turn this thing on? When you do f.compile, you can either just do compile, and then you will get whatever the environment supports. In this case, I'm just running plain .NET Core in a console application. It will use JIT compilation. If you would run the same thing in, for example, a Windows Store application, you would have a different behavior there because we have some more constraints to work with. But, you can always override this thing and say prefer interpretation true or false, I won't like this thing to be compiled, which means JIT compiled, or I would like the generated code to be interpreted. And it turns out that this interpretation option is actually useful in a bunch of other places as well, where it's not constrained. A good example of that is if you have a small expression. For example, in some library, you use expression trees in order to instantiate objects, and you're just going to call that thing once or twice. Like if it's something that you will want to call 1,000,000 times, you definitely want it to be compiled, because then ultimately it becomes native instructions and it runs at CPU speed. But the cost of compilation is non-negligible. Like, we have to spin up a lot of machinery deep down in the CLR in order to be able to do that. If you turn on interpretation, it will be much faster to get to the delegate, but the resulting delegate will be slower to execute. If you have to do it 1,000,000 times, it doesn't get better over time, right? And so now you have this dial that you can sort of, move around. If I'm going to invoke this thing only a few times, maybe interpretation is a good option, because it will have less overhead to be able to compile this thing. And so this is actually interesting because, let me try to run this thing. Come on, start, there we go. The reason that I was actually saying it doesn't want to start for some reason. Why doesn't it want to start? There it is. Just have to talk to it more. Some speech recognition, I guess. So here you go. What's interesting about this little puppet here is that I'm just clicking through something here. Don't have to worry where that is. Well, let me actually put it over here. Is that you can actually inspect, the interpreted code that we generate, and you will see some little thing that looks a little bit like IL. Actually, I helped out a lot on this particular feature to help optimize it and implement it. But if you take a look over here, this is actually the purest, stack evaluation machine you could imagine. Like, if you sort of want to see, a standard academic style, implementation of an interpreter, this is actually a beautiful reference implementation. It's something that's really simple on the face of it. The way it works is just a stack machine. We will load objects, we will pop things, we will push things. Like, we don't have to turn things into assembly instructions. We literally execute things in a stack-oriented fashion. And so you can actually go to this to the code as well if you're interested. But it should be something, if you look at it, you will say, well, we could come up with that as well. So over here, for example, the add instruction, the way that the add instruction works for, say, 2 int32s is, we get access to some stack, which is just an array at runtime, an array of objects, and we'll just, pop a couple of things out of that array by indexing into the stack at -1 and -2. We'll do something to add those two values together. This can also support nullable values, so we have to do a bunch of null checks. But then ultimately we push the new value onto the stack by substituting, the operand, at position -1 with the ultimate result over here. So really this is a slightly optimized piece of code because we index into the stack directly. But if you would go to source control here in GitHub and look at the history, you would actually see that originally it was doing something like 2 pops followed by an add and then a push. So it's actually the simplest way of implementing a stack-oriented evaluation machine in a very similar way that your calculator works, like a classic calculator where you do 1 enter, 2 enter plus. That runs in exactly the same way. But so all of that stuff is available. You can take a look at that, and it actually has a use. You can, if you compile a lot of expression trees, you don't want to execute them very often. You just want to, evaluate them a few times. The interpreter is now a new option that you have available. And in fact, in the Bing stack, we're using this in a whole bunch of places where we sort of quickly have to evaluate something that doesn't stick around for very long. In the past, we had to spin up the expression compiler, which talks to the JIT inside the CLR, which requires some heavy locks. Was a pretty expensive thing. If every single request was doing that, you're kind of compiling code at runtime all the time. Now we can, in certain cases, use interpretation, which has been very beneficial in certain places. Okay, so that's a little bit of the core FX side, and I wanted to spend 2/3 of the talk actually in this space. Now we're going to take a look at the core CLR as well. So one thing I wanted to show you that you've maybe seen when you were actually browsing source code in the past or using ILSpy, is that sometimes you actually end up, now where's math? Oh, it's on the other side, I'm sorry. That sometimes you actually hit a brick wall. So I'm going to open the core CLR now. Over here, this will take a moment. But as I'm explaining this, let me open ILSpy as well and sort of show you the experience you had in the past if you wanted to learn a little bit more. So as you were looking at some code, let me open up something else in the meantime as well to get some concurrency. A site you should also have next to your home page, which should be github.com/.net. The second tab that you should always have open is source.net. That's actually the reference source page where you can actually just browse, the source code. And so the file I wanted to show you is, for example, math.cs, which contains all of, the math functions. And so here you had typically in the past a hard time to sort of get through the brick wall. You will see that in system.string, you will see that in system.object, you will see that in system.text.string builder. A whole bunch of places you will see internal call. And in the past that was the end. You couldn't go much further to figure out how the heck does this thing work. You could maybe noodle around in WinDebug and do a native debugging session and try to step into it and look at the assembly if you're really ambitious. But now you can actually go through this brick wall. And so I will actually show you how you trace things from core fx, where it says internal call, to the corresponding code on the other side. Okay? So I have core fx open over here, core CLR, sorry. And where I'm going to go is some file called ecall list. Ecalls are the internal calls, and you see that I was actually there a moment ago. This is actually a table, and you will see we're now in C and C++ land. Core CLR is actually a repo that's full of macros. This doesn't even look like C. You see fc func start, fc func element with a whole bunch of commas, all macros. This was written, in the late 90s, and, macros were the way of doing a whole bunch of things. But you see over here, for example, that the square root function actually refers to something called com_double. And com_double also goes back to the history of the CLR, which at some point was conflated with com+, the next version of the component object model. And so you will see a lot of references to COM and core for common object runtime. So you can sort of really start seeing history bleeding through over here. And so, for example, if you do math.cosine or math.square root, it will actually go to this com_double sqrt function, which you can also, of course, browse to. And so what I have here is the core CLR. And I'm just sort of going to skim over the repo very briefly here. But the main areas that are of interest is the VM, which contains the JIT, for example, also the type system and all of that stuff. So if you want to see what we do in order to generate, for example, this rotate left instruction for hash codes, you will actually find that in here somewhere deep inside the JIT code. We're not going to spend too much time in that space. But we also have, for example, ClassLib native. And ClassLib native is actually the native side of a bunch of types that you see on the managed side. For example, BCL type over here, you will see the native view on the decimal type. So you will see how the decimal type is implemented. This actually contains all the code of like doing adds and subtractions and comparisons with decimals. You will also find stringbuffer.cpp, which is the backend of the string builder class. As you can see over here, so that's actually how that thing is implemented. But the one I wanted to look at just very briefly over here is float double. So that's the one that contains the square root function, for example. And here you see a lot of documentation. And that's one thing that's super nice about the core CLR and the core FX repo. There's a lot of stuff to read. In fact, I would recommend you to do the following. Just, go to the command line and find anything that starts with / and just print it out. You'll have 500 pages, and you will just read beautiful stories about bugs that were solved in an epic way on Christmas Day in 1997. You will find like a whole lot of, interesting stuff. Now, this one is pretty interesting because the desktop CLR in the .NET framework actually has a bunch of these things built in. We have something called JIT intrinsics. If I would do the same exercise to go and see how does interlocked exchange work, you will actually not find an eCall list that points to some C function that does that, because the JIT compiler will see, oh, they want to do an interlocked exchange, I need to change that into a CPU instruction when I'm generating native code. In the past, things like square root and sine and cosine and those things will also directly go into assembly instructions, but that actually reduces portability. And with .NET Core, we actually want to be super portable. So something that people did over here, and you see a whole bunch of explanation here. In the past, we implemented this using a JIT helper in assembly code, and we had to do it 3 times, once for x86, x64, and once for ARM. But nowadays, in the past we did that because the C runtime that we use was not fast enough. But now it actually turns out that the C runtime does a very good job at actually executing that code as fast as you would be able to do it if you were just emitting assembly instructions. And that also helps to make this code super portable, so that it can run on Windows, it can run on Linux, it can run on any operating system that we want to target in the future. So this has now just been changed to the C runtime. And so if somebody asks you, well, I use C++ because, I want to use the C runtime and it has a super efficient square root function, well, you can now say, if you write math.square root, it does exactly the same. We'll just turn it into a call to the square root function in the C runtime. And so now you can actually start tracing through those boundaries where in the past you hit the brick wall. How does this thing work on the native side? You go to the eCall list, you look at the member name, and you see the corresponding native code on the right-hand side. So things like string.substring, for example, string.length, those things sort of go over that brick wall as well. Okay? So that's one little thing that I want to show you. Now, there's a whole lot of code here. There's too much to read in a lifetime. But so what you can, well, maybe not in a lifetime if you just, move to Nepal and just, sit in a monastery for the rest of your life. You could do that. But one thing that I would recommend you to take a look at if you're really interested in how, for example, the CLR works, is the book of the runtime. And the book of the runtime is something that existed internally, was originally written in 1997 when the CLR development started. It was only shipped in 2000, 2001. So, the work dates a lot back. And, it wasn't very updated to the actual state of affairs. But so we actually took the book of the runtime and actually translated it completely to Markdown files in GitHub. And you actually see over here that, for example, some description of some stuff in the just-in-time compiler was changed 4 days ago. So this documentation is actually kept up to date quite well. You see the profiling API 14 hours ago, somebody updated the documentation a little bit. There's some stuff that doesn't change that much, the way that exception handling works, for example. Well, a year ago that was changed, but you can actually browse to a whole bunch of things. And so I'm just going to show you one of those docs about a JIT compiler. That's arguably the most complex piece of functionality besides the garbage collector. Those are the two more complex things in the runtime. How many of you have actually seen com+ variables in the past in documentations? Com+ underscore. I see a couple over there. There's actually a bunch of things that you can set in the environment to influence the behavior of the runtime. And occasionally we document some of these in the past. Somebody runs into a performance issue. Oh, you can set that com+ variable in the environment, and it will pick up on something, and the runtime will do something different. Well, in fact, this thing shows that there is a feature, which I'm not going to show now, but you can just enable that thing on a private build of Core CLR. You can actually turn on something called JIT dump. And if you turn on JIT dump and you just run a function that adds 2 numbers together, you will have 100 pages of output. It will basically document everything the JIT is doing to register, allocate things, to look at the tree and so forth, and you will end up with output that looks like this. And of course you have to read this document to be able to interpret it, but it's no longer a black box. You can turn on that thing and start learning phase by phase, what the JIT compiler is doing to come to the conclusion that the most efficient way to add 2 numbers together on your platform is by emitting that piece of code. So something to look at, and in fact there's a section over here called setting configuration variables where we have, oh, that's actually a whole bunch of these, but there's another link somewhere here to CLR configuration knobs where, we publicly document, there's no secrets anymore, like, a list, and I can go on and on and on and on, like of a whole bunch of environment variables that you can set to actually gain insight into how the thing works, and also, influence a whole bunch of things, like certain behaviors of the garbage collector can be influenced and so forth. So the key here is read define manual RTFM, okay? So that's that. One last thing I'm actually going to show you very briefly is something about a GC. The garbage collector is a pretty involved piece of logic, but it's actually not that complex at the face of it. What I mean by that is that it has a very, very well-defined interface with the execution environment. So what's really happening with something like GC, and I hope you've heard this story before, is that when you allocate something and there's no more space, we have to kick in the garbage collector. And so there's two interfaces to that. One thing is the CLR says, I want to allocate some memory. The garbage collector is not just the thing that collects garbage, it's also the thing that's responsible to allocate blocks of memory. So that's the interface of the CLR to the garbage collector. But then there's also the opposite interface from the one that I'm showing here, is the GC to the CLR, where the GC says, well, I would like to allocate something, but we are out of space. I would like you to stop for a bit so that I have some quiet environment here, pointers are not going to change, suspend the execution engine, I can now start collecting garbage, and then I want to restart the execution engine. So you will actually find two interfaces here. The interface of the GC to the execution engine to start and stop, and actually walk pointers to know, like, is this actually a reference type, is this a reference type? And then the opposite way, where, in fact, when you do something like a new expression in C#, it actually turns through JIT compilation into a call to the alloc function over here. If you want to alloc something that's larger than a certain size, you will actually have an alloc on the large object heap, alloc L heap, and that's the opposite interface. So it's a very small set of interfaces here. There's a bunch of accidental complexity, of course. But one thing that's very interesting is that there's a Hello World application here that doesn't use the CLR at all. This thing runs the garbage collector as a separate component in a fake execution environment. This is a complete pluggable component, just like the JIT is completely pluggable. So there are some very well-defined, pretty tiny interfaces between different components that can actually help a lot to sort of form your mental framework of how does this thing work. Like, it looks like one big black box, but internally there's a lot of subcomponents and they have very crisp interfaces between them. And so this sample over here is literally a C console application that just runs the garbage collector without anything in the core CLR. It actually mimics, doing allocations. You will see the suspends and resumes coming in. And so you can actually run this thing to sort of see, like, how do those two things talk to each other? Like, what does the GC want from the CLR? What does the CLR want from the GC? Similar things happen for the JIT compiler. And now finally, I also wanted to show one more thing, the last thing. Reading this kind of code is also fun. Let me actually try to find it. Here we go. This is actually the back end of system.object, the thing that's responsible for hash codes and equality and toStrings and that kind of stuff. I wanted to talk a little bit about the hash codes and the way we actually generate hash codes, but we're pretty much out of time here, but that's the place to actually go. Now, one thing that's interesting is that the CLR people are also a funny bunch of people. You see over here that there's a to-do, and there's a to-do for something copy on write related. So they defined cow for copy on write with value 4, and then behind that it says moo moo, no, not bovine, really copy on write. So sometimes you will find super dry humor in here, like, oh, there's a cow in my code. Is that really a cow? No, it's not something that will do moo. It's actually the abbreviation of copy on write. And I think, if you see that comment once, you will remember, that this thing, oh, there's something about copy on write here, has nothing to do with cows. And so we have a lot of acronyms, and some of those acronyms have some funny explanations next to them. we may want to clean that up at some point, maybe it doesn't look that professional. But, what really happened is that a whole lot of code, ever since, the mid-90s, was actually moved into the open space. We did very little scrubbing on that code, maybe some references to internal bug databases that don't have any meaning to you guys. But, there's still a lot of stuff in here. And in fact, a lot of this stuff contains historical notes on how things are designed, how things are written, why certain decisions were made, what performance characteristics are. So you can actually, have a lot of fun reading those things, which used to be black boxes. And, in the past, you may go to some internal talk, or you may actually pick up a book. And at the end of the talk, you couldn't do anything else. You could maybe watch the talk again, and that's it. Now you're actually super empowered. You can actually go to that code. You can actually literally hit build.cmd and build your own copy of it. You can step through that code if you like, or you can just occasionally say, I'm really curious how this thing works, and maybe spend 1 hour and get enlightened and maybe pick up on a couple of other things that you see in there. And it's really, I think, a fun thing. It's a way for you guys to stand out at your company, as the one that knows like how this stuff works, as opposed to those people who just sit on the top of all of it and, just build some UI application, and at the end of the day, it is what it is. Like, I would say go to the internals, figure things out, have a lot of fun, and don't be shy. There's a whole bunch of people contributing to .NET Core. You can do pull requests over here. You see there are 64 pull requests on the Core CLR. There are 49 on Core FX. We're actually very eager to take in pull requests. We listen to a lot of issues. Like you see, there's 2,000 issues on the tracker over here. There's 1,400 over here. So, you can now be heard, but you can also be empowered. You can actually come in, fix something, and in fact, if you look at the release report of .NET Core 2.0, there's a lot of kudos to people in the community helping to do things like, there was this community guy who improved like NQ and DQ on Q of T, the performance of those guys. Like, everyone benefits. The guy had a lot of fun doing it, gets recognition. So go in there, take a look at the nuts and bolts of Core CLR and .NET Core and have a lot of fun. With that, I'm at the end of my talk. Later we'll talk about .NET performance, and even later we'll talk about how to build your custom analyzers and code fixes in Roslyn. With this, thank you very much.